Agentic coding is directing an agent to write, run, and revise code on your behalf. It is not passive. You are not a bystander watching the agent write a program. You are the author who has contracted out the typing. Every file the agent creates, every function it writes, every import it adds is yours and will be submitted, run, and rerun on a clean machine. The risk is not that the agent writes bad code. The risk is that you stop reading. This assumes you are comfortable operating a rig and prompting an agent. Here is the ground we cover: the loop that structures the work, the oracle that makes it converge, directing the agent with precision, reading the diff it produces, pinning a reproducible environment, and keeping a version history you can trust. Agentic coding proceeds in a cycle, alternating between your direction and the agent's execution. First, specify. State clearly what the agent should produce: a function, a script, a test, with explicit constraints on interface, style, and correctness. Then execute. The agent writes the code, runs it if appropriate, and reports the result. Then read. You read the changes the agent made through diffs, file inspection, and testing. Then commit or revise. When the change is right and understood, commit it. When it is not, give corrective direction and go round again. The process is deliberately incremental. Each cycle should produce a small reviewable change, not a 1,000-line scaffolding dump. Because a change you cannot fully read is a change you do not own. What makes the execute step more than fast code generation is the verification oracle, the interpreter, the test runner, the compiler. The agent can run on its own output. In a chat interface, this code runs is a prediction. In a rig, it is a checked fact. And a failure returns a structured signal: the line number, the type mismatch, the stack trace, telling the agent exactly which assumption was violated. That is why the loop converges even when the first attempt is wrong. Each run, fail, fix cycle is grounded feedback, denser than any specification you could write up front. The oracle is not always binary. A biochemist segmenting cells or an immunologist normalizing an assay checks the output against a known test set, a few hand-annotated images, a control sample of known concentration. That the script runs is the first oracle. Whether the answer is right is a second, graded one, a number the loop can act on. And whether the workflow suits the problem at all, that is not a test. It is judgment, and it stays yours. The same oracle, formalized as a scoring function, becomes the evaluation harness you build later. This gives the first working principle. An instruction that says, implement the entire pipeline, produces code faster than implement the data loader, then stop. But the first is harder to verify and harder to correct. Small steps compound correctly. Large steps compound errors. A wrong assumption early, buried under 1,000 lines, is far more expensive to find than one caught in a 10-line diff. So the principle is plain: prefer small, reviewable changes over large, opaque ones. The quality of the agent's code is strongly predicted by the quality of your direction. 3 habits carry most of it. First, specify the interface before the implementation. Not write a function to score a model, but the name, the parameters, the return type, and the invariants. Score takes a model and test arrays, returns a non-negative error, and raises exceptions on incompatible shapes. A precise interface constrains ambiguity, though it cannot rule out every misunderstanding. Second, cite the files that matter. Not extend the loader, but modify the load_dataset function in sourceloader.py. Otherwise, the agent may edit the wrong file or duplicate code that already exists. Third, 1 task per instruction. Add a loader, write its tests, and update the docs is 3 tasks. Bundle them, and if the tests are wrong, reverting them reverts the loader too. 3 separate instructions each produce a single-purpose change you can review, accept, or revert on its own. Now the habit at the center of it all: reading the diff. A diff is a compact view of what changed between 2 versions of a file. Lines added are marked with a plus, lines removed with a minus. Here the agent has added a CSV branch to a loader. 4 green lines. If the path ends in .csv, read it with pandas, split off a column named target, and return features and labels. It runs. The tests, if there are any, may pass. But read it. The branch assumes the target column is named exactly target, and that every other column is a feature. Neither assumption is in the instruction. Both change whether it is correct on real data. And it quietly introduces a dependency on pandas, the PD alias, which must already be in the environment. Far better to catch that in the diff than at runtime on a clean machine. Reading every diff does two things. It catches the errors that are invisible in the output but legible in the change, and it keeps the codebase yours. A researcher who reads every diff understands their own work. This discipline has a name: diligence. Never let the speed the agent offers cost you responsibility for what remains your work. Code is reproducible when anyone can clone the repository, follow the documented steps, and get the same result. Three things make that true. First, pin the dependencies, not NumPy and scikit-learn, which lets a collaborator install a different version and change your numbers, but exact versions, NumPy 2.1.3, scikit-learn 1.6.1. Second, isolate them. A virtual environment is an isolated install holding only this project's packages, so versions cannot collide with another project's. Third, and optionally, reduce it all to a single command. One command that installs, loads the data, runs the pipeline, and reports the result, with no manual steps in between. If an evaluator cannot reproduce your result with one command, the work is not reproducible. One honest caveat: pinning is necessary, not sufficient. The same model weights can give different outputs across a serving stack, and a resource-bounded container's budget is itself a variable. Reproducibility pins the environment, not just the version list. Last, the version history. An agent given latitude produces long sessions of changes. Your job is to organize them into coherent commits. An atomic commit contains exactly one conceptual change, so each commit can be understood, reverted, or cherry-picked on its own. A cohesive change and the tests that verify it are one change, not two. Split them, and neither commit passes alone. The aim is coherent, tested, and independently reviewable, not merely small. Before committing, ask one question: if I need to undo just this one thing, can I? If the answer is no, because the commit bundles two unrelated changes, split it and write the message to say why, not what. The diff already shows what changed. Not fix bug, but score on the validation split, not the full dataset, which was leaking into fitness. 6 months later, you will be grateful for it. Here is agentic coding on one card. The loop: specify, execute, read, commit. The oracle: a checker that makes the loop converge. The diff: read every one. The environment: pinned and reducible to one command. The history: atomic commits, messages that say why. And the key idea to carry away: the agent types, but you are the author. Read every change, ground it with an oracle, and own the result. The speed is only worth having if the work stays yours.